option. If you don't want to write down Van der Waals process of adsorption, okay, you can write down induced dipole, induced dipole. You can see Van der Waals process, induced dipole, induced dipole, and also mention that the covalent bonds are stronger than the induced dipole, induced dipole. Okay, you have three options over here. Any one of the options were accepted by Cambridge. Keep on moving. They explain why increasing the total pressure constant increases the rate of production. Now, this is rate of reaction. Cambridge is going to try to get you confused. The same concept is used for O level also. Get you confused between Le Chatelier's principle and rate of reaction. Over here, it is talking about the rate. Okay, so the rate is rate. Where we have the yield, it is Le Chatelier principle. Okay. I hope that you got the answers. Okay, because it is easy to lose one mark. You can see that 1 mark is given for the closer together. The second one is about the collision. Okay, and then for the yield, it is again showing where it is going to move, okay, and why it is going to move. Okay, so you will see that in the equation I have written that here we have 3 moles and here we have 2 moles. Now we could have also got an explanation about temperature, because over here the reaction is exothermic. So you have to remember that when we increase the temperature, it would have gone to the left hand side, and decrease the temperature, it would have gone on the right hand side. So please just work that also in terms of temperature, and you can also work it out in terms of concentration, where for concentration it will be same as pressure, because when you increase concentration, it is same as, that is, when you increase pressure, it is same as increasing concentration. Okay, here now a new type of question, okay, but it shows to you that it is not reaching 0. So as the concentration of the cheese are not reaching 0, shows a reversible reaction which has reached equilibrium. Okay. Now in this question, the first part, explain why the gradients of SO2 and O2 lines decrease with time. I would just write it down. Okay. I'm just talking about the reactant. So for the products, let's write down maximum product, maximum Now, what I would like you to do in your paper, if you have hard copy, if you don't have, then afterwards, when you can just do it, you draw a tangent at the beginning. Okay, draw a tangent at the beginning here, draw a tangent at the beginning over here. Then you draw a tangent somewhere around here. Okay, I hope that you're understanding. You draw a tangent initial and a tangent after some time, and then what you do is you look at the steepness. You will find that the steepness is more in the beginning. Now, this is a Form 5 type of question, but only thing that has changed is that there is a reversible sign and that a graph has been given. Okay, so we have learned as from Form 5 that we have maximum of the reactants at the beginning, so we will have maximum collision, so the rate will be faster. So this is what all we just had to. Okay, so we had just to draw the tangent. Please, those have hard copy, draw the tangents to find out that there is a change in the steepness. Okay, so in the beginning, like I have written down over here, highest change in the beginning as we have maximum reactance, so we have fastest reaction at that moment. So as time is moving on, amount of reactance is decreasing, rate is going to decrease. Explain why all these three lines become horizontal. You verify your notes on Le Chatelier's principle. You have these graphs over there where we have seen that we have reached dynamic equilibrium where the rate of forward and the rate of backward reactions are the same. Suggest a reason why the initial gradient of the SO2 line is steeper than that of the O2 line. Okay? So again, if you would have drawn the line, it would have been easier to try to find out. So just understand that over here from the reaction, we have 2 moles is reacting with 1 mole. So anyway, we are going to use twice. At any speed it was going, we are going to use twice the amount of SO2 compared to that of O2. Okay, keep on moving. Right. A question on Kc, where Kc is equilibrium at terms of concentration. We are concerned in terms of concentration, where it is number of moles present at equilibrium to the power of n, where the power of n is the number of moles divided by the reactants present at equilibrium to the power of n. Now, I have not worked it out. We are going to work it out together. But what I have just done, I have just put the initial part. So we had 2 moles of SO2, 2 moles of O2, SO3 we did not have any. And then the number of moles at equilibrium, we only know that of SO3. Okay, so SO2 produced, SO2 used. These 2 moles is to 2 moles. So 1 mole is to 1 mole. So if I have got 1 mole of 1.98 moles of SO2, I would have used 1.98 mole of, right? So I would have used 1.98 mole of SO2. So how much is remaining? It is 0.02. Okay. Now, if I have used, just come over here. So SO2 is to O2. Take these 2 moles is to 1 mole. 1 mole is to half mole. Okay. So if I have used 1.98 mole here, it will be 1.98 to 0.99, 0.99. Again, we just clarify it. This is used, and this is also used. So 2 remaining. Is 2.00 retiré 0.9. N.0n. So here, this is, let's write it down here, S2. Okay. So I hope that these are the answers. So here, 0.02. And here it is N.0. What we have to do, we have to calculate Kc. Kc equal to creation of SO free to the power of 2 should be divided by concentration of SO2 power of 2 multiplied by concentration of 2. Now, many students make mistake over here. Sometimes, by coincidence, the mistake does not make you lose marks because the concentrations cancel. So a student has to understand that concentration equal to moles per mole. sometimes if you have two species numerator, two species denominator, it cancels out, so you don't find any mistake. But over here, we have to the power of 2 and then to the power of 3. If you look at to the power of 2 and here to the power of 3, numerator and denominator, so we have to be very careful. So S of 3 is 1.98 divided by 40. This 40. Yes, 40 dm cube to the square. Let's not forget to the square. Here it will be 0.02 divided by 40 again to the square, multiply by the units, the value, we are going to look at it afterwards. You must have the value as well. Cube bracket here. Square. It is going to cancel out with the mole per dm cube. To the square which is present in the numerator, and sorry, in the denominator, but we have another mole per dm cube which remains. Here we are going to get, therefore we are going to get equal to 1 upon mole per dm cube, or 1, depends on how you're writing mole per dm cube. Okay. Finally, the answer becomes dm cube per mole. Always write down per mole at the end. Okay, so here the unit will be dm cube per mole. I think the value I have replaced it properly. Oh, I made a mistake here. It's divided by 40. Okay, I need to divide by 40, right? So the value, just give me 1 sec, I'll just calculate it. Okay. So the value is coming to 3.882 fois 10 à la puissance de 5 as per the marking scheme. It's coming to 3.882 fois 10 à la puissance de 5. let's move on. Now, structural isomerism. Here, I have some details to add. We are not just going to look at the definition, because I hope that the definition, this is from directly from your copybook, okay, or your notes, okay. But what I want you to understand is that here, structural isomerism, it is chain isomerism. That is chain isomerism, straight chain O as a branch. Yeah, I hope that you understand what is has a branch. Like you have two methyl. This is when you have a branch. Then for structural, it is also positional isomerism. Now, what is positional isomerism? It is example, you have propan, prop 1-ene, this is propan 1. Like this. One propanol or 2 propanol. So here it means that the position of functional group is this is known as positional isomerism, chain isomerism, and also you have functional group isomerism, like alcohol, ether, aldehyde, ketone, carboxylic acid, and ester. You can also have alkenes and cycloalkenes. Next over here, stereoisomerism. So stereoisomerism is cis trans and optical. You may get questions where you have to give examples, okay? Now, how to understand it? Let's see. Different spatial arrangement of atoms. Here you have different structural formulae, different structures, okay? But here you have different arrangement of atoms in space. So when you arrange it differently, you can get cis-O, trans, or you may even get optical. Now, why pent-1-ene does not show stereoisomerism? Pent-1-ene is an alkene. Now, here I have told you beforehand that CH, go to the easiest one, CH2, and CH3 and C double bond C or never chiral. So you can see that in pent-1-ene we have these parts which are included, so we will not have optical isomerism. Also, for cis trans to be present, we need to have, I write it like that, to be present. I'm not going to write it down. Why waste time? Okay, it is already here. We should not have the same groups. So same groups are attached. Okay, yeah. Now we can move on. The monomer, we need just to have a double bond over here between the carbon-carbon atoms which are horizontal. This one. So you could have shown it in any way, how it is, okay? This is one method of showing it. I would have preferred you go to the simplest way. You put the H here, CH3, and C2, CH2, CH3 down here. So H, CH3, C2H, 5. Okay. Now, so that compound, when you place it over here, it becomes 2-methylbutanene because you have to count the longest number of carbon atoms. 1, this becomes 2, this becomes 3, and this one becomes 4. That's why you get butanene. Okay. Now the double bond will be here, so this part will be known as the terminal carbon. Okay. Not the terminal carbon atom, so it is the carbon atom with lowest number, because the double bond will be closest to it. Carbon atom with lowest number. And then you can see at the carbon which is number 2, we have a CH3 which is attached. So this gives the methyl. So 2-methyl, 1, 2, 3, 4 butene. Why 1? Because the double bond is over here. It is in the terminal. That is, it gets the lowest number. Draw the structure of different isomer. Okay. So here I think I made a mistake. Cannot be. Of C5 H10. Okay. So C5 H10. I made a mistake here. Cannot be pent-1-ene. Has to be pent-2-ene. Because if it is pent-1-ene, it won't be cis-trans. Okay. So either you draw the cis or the trans. Okay. I'm going to show you the example of the cis. So this is a cis. Okay, you can see that 2 H's are above the ground. The groups which are below, no need for them to be the same. I think, taught you that last time. They can change. Okay, at least we have the hydrogens on top. This is cis pent-2-ene. And then next, you could have also drawn the trans, because nothing has been said if we have to draw the cis or the trans on only. So this is the trans pent-2-ene. You can see the H's are diagonal to each other. Okay. Now, next question is about group 7. Morning time, I have sent you some videos, okay, all related to what we have to talk about, be it SN1, be it Markovnikovs. I have shown you some, I have sent you some videos, okay. I have viewed them. They are good videos. There are some of the stuff which are not in your syllabus, but at least it helps you understand what is going on. We are going to skip part A, part B, part C. We are going to skip. I hope that you know what we are talking about. We'll come to the part D. Okay, this is what I have sent in one video. With the chlorine, you can see that you get only the acidic gas of HCl. With bromine, you get the acidic gas of HCl. You can get some color change. With iodine, you get mostly, okay, very little amount of the acidic gas of HI, but you get H2S, which is being produced, and you also get SO2. Now, instead of potassium dichromate, you can use what is known as potassium permanganate. It will be purple to colorless. Instead of lead acetate paper for H2S, we say that we get a rotten egg smell. Okay, HSC students, this is from group 7. Lower students also from group 7. Whatever details is being asked by Cambridge over here, it is given in your notes. Now, oxidizing agent, it is an electron acceptor. Now here I just wanted to write down, so here the oxidation that's something 0. Here it will be -1. Okay, here now +1 plus x minus 2 equal to 0. X minus 1 equal to 0. X equal to +1. Hope that I have not done any mistake over here. You can confirm it. So OCl so here it is +1. Okay, so this reaction is known as the disproportionation reaction. We have done it in both the classes, lower and upper, in the topic electrochemistry, where disproportionation reaction, one molecule, okay, or one species is oxidized and reduced. In fact, this disproportionation reaction, Cambridge has given another question where you have to write again the equation and then talk about it, where you can see from chlorine, which is here 0, here it is -1, here it is +5. So here Cl Cl2 Cl in NaCl. This is easy to calculate. I'm not going to do the calculation. It is -1. And Cl in NaClO3. Now, these equations, they are very important equations. In fact, you have chlorine with cold aqueous sodium hydroxide and chlorine with hot aqueous sodium hydroxide. The reactions are the same. That is, here you get NaCl and water. With cold also, you are going to get NaCl and water. With hot, you get NaClO3, but with cold, you get only NaClO. So remember, with hot, the reaction goes further, and when the reaction goes further, you have more of the oxygen. So here it is +1 plus X minus 6 equal to 0. X is equal to +5. So this reaction shows that chlorine over here is reduced, okay, and over here it is oxidized. We come to the next question. 2-bromobutane, okay, where when we have 2-bromobutane, so here we have we call it a secondary halogenoalkane. A secondary halogenoalkane is always going to give me a secondary alcohol. We had discussed this part. Okay. Now, for me to get an alcohol, the NaOH should be providing with OH minus. So this NaOH should be in the aqueous state. This will be N. So when we count over here, 1, 2, 3, 4. Move this down. This will be 4. 4, 3, 2, 1. There are many ways of looking at it. Okay, a student who's good with symmetry can see that there is a line of symmetry over here. So if there are 2 before, there will be 2 after, and automatically it is going to get the name which is related to the 2. So here the name will be 2-butanol. Okay, it is a secondary alcohol. When it undergoes oxidation, where the potassium bichromate changes from orange to green. Okay, here we heat under reflux. There is nothing to worry about distillation or heat under reflux as compared to aldehydes. And here we are going to get a ketone. Okay. Now we come back over here, C4. 3, 4, 5, 6, 7, 8, 9, 10. Yesterday only we spoke about it. What is the difference between an alcohol and a ketone? You will see that the ketone has got less of, okay, of hydrogen. How many? Less 2. Now, the C double bond O will always be in the middle. So here it is going to become CH3. C double CO, CH2, CH3. Okay, because remember well, a ketone is RCO, R, where R cannot be H. Okay, R cannot be H. What else over here? C4H8, so it is following the CnH2n. When it follows the CnH2n, it is an alkene. Okay, this NaOH should be ETH. ETH means ethanolic. Okay, now here you can remove the Br. So Br has to be removed, elimination. So minus HBr. So if we remove from, if H moved from left hand side carbon, we are going to get CH2 and the double bond, and CH and CH2, CH3. I hope I've not done any mistake. If I have done any mistake, just let me know. So this one, 2, 3, 4, 1, build 1 in. No cis trans. Okay. No optical. If H is removed from right hand side carbon, right side, get here, then I'll get CH free, CH double bond, CH, CH free, CH double bond, then CH, CH, CH free, CH double bond, CH. Okay, this one will be but 2. This trans iso. Peaceful. Cis trans isomerism will be present. Okay, so here we will have the cis trans isomerism. So I hope that ketone, everything has been written over here. Free structural isomers of A. So A now is spot here. Question number 4. So here it is. First one, 1, 2, 3, 4, 1 bromobutane. So I'm going to just to write it. Yeah. So the first one is 1 bromobutane. It is a primary halogenoalkane. Okay. The second one, and it is a straight chain. Let me straight. Okay. It comes in the isomerism that we spoke earlier, okay, which is here, structural isomerism. Okay. In the earlier question, structural isomerism. Then number 2, we have 1 bromo, 2 methyl, and 2, 3 propane. So it is 1 bromo, 2 methyl propane. It is also a primary halogenoalkane. It is also a primary halogenoalkane. But here it is a branched. And the third one, 1, 2, 3. So 2 methyl, 2 bromo propane. 2 methyl, 2 bromo propane. This one is a tertiary halogenoalkane. Okay. Tertiary halogenoalkane. So when it is a tertiary halogenoalkane, if it undergoes a certain reaction, this one is going to give me gives primary alcohol, give NaOH AQ. This one also is going to give me a primary halogenoalkane with AQ. I can add up something which is branched. It will be a branched one because in the halogenoalkane itself we have a branch, and then this one is going to give us gives a tertiary alcohol with NaOH. Move forward. Mechanism SN. Okay. In the videos that I have sent you, you have it. One means unimolecular in the slow step. Okay. So when you have S and Q means nucleophilic substitution bimolecular. Now, SN2 is mostly undergone by primary halogenoalkane. Please go through the videos, okay, or else you won't understand what I'm telling you. It is because the OH, when it is approaching the halide, it gets repelled because both of them are negatively charged. It goes at the backside. We have small hydrogen atoms, so it can react with it, and this reaction takes place in the slow step. Then you can change the concentration of the halogenoalkane. You can change the concentration of the NaOH. It is going to affect the rate of reaction. Okay, but in SN1, it means that we have a tertiary SN1. SN1 is mostly undergone by tertiary halogenoalkanes, because the halogenoalkane does not have space for the nucleophile to come to attack, because we have large CH3 groups which are attacking. Now, a secondary alcohol, not alcohol, but secondary halogenoalkane can undergo both elements. Okay. The secondary is different. It can undergo both mechanisms. Okay. You look at the video. Okay, the BR. Wait. So the BR is pulling the electrons towards it. Okay, the BR is pulling the electrons towards it. The carbon becomes delta plus, and there we have delta minus, right? And then the OH is coming to attack the carbon, which is delta plus. Now you can see that this carbon, okay, here, it is called a secondary carbocation. Why it is called a secondary carbocation? Because we have two alkyl groups over here, CH3, over here, CH2, CH3. Okay, so this is an alkyl group. This is the second alkyl group. We have two alkyl groups which are attached to it. Each one of them are pushing electrons towards it. I have also sent a video which is talking about Markovnikov's rule and the carbocations. Okay, so please have a look at the videos. Next, also I have sent a video about the reagents. Okay, not the reagents, but the rate of reaction of secondary halogenoalkanes, where you have chlorine, bromine, and iodine. Listen to it carefully, watch it carefully, because it is not that clear, but you can see that the yellow precipitate is formed fastest. Why that's so? It is with respect to the bond, okay, the C bond. Okay, so here you can see that CCl 340, CBr 280, but Ci is 240. So Ci breaks more easily. Last part. Okay, we all know that for elimination it is ethanolic instead of aqueous. Now, last time a student had come with an idea of using NaOH and KOH. So if you have to give your own reagents, then you can use NaOH, like you keep NaOH for hydrolysis over here. So the nucleophilic substitution, you keep NaOH aqueous. For the elimination, you keep KOH ethanolic. But you see over here, Cambridge is not giving you two different reagents. That's why sometimes it is better to go with the same reagents, but to know the conditions properly. Okay, so this ends up this paper. Now, for tomorrow, we were supposed to have a session. Okay, that session, we will keep it for 6:30 in the evening. Okay, 6:30 in the evening. If I'm canceling it, I will let you know. Okay, but it won't be during the daytime because I'm working for arts paper for Cambridge. So I don't want to lose a session. So we'll keep a session 6:30 in the evening. If I feel that I can't give the paper, I can't come and correct the paper, I will let you know. But 6:30, just one sec, in the evening, if we can do the session, just checking something. It will be June 2019, paper 21. So we are going to keep for June 2019 paper 21. How many papers we have for we have 3 different papers. Yes, we have 3 different papers, and the papers are not as easy as the June 2018 ones, a bit different. Okay, so try, we'll work it out for tomorrow. Now, some of you, please, be it lower or upper, because there are some upper students, it says they are not sending me their marks. Okay, I'm not going to take the names. Okay, so do send me the marks that you are getting, at least for, especially for upper students. At least we will know. Okay, I will know what's going on. Okay, how is your progress going on? Okay, so as soon as we log off, please send me the paper. If someone has recorded the session, please post the link. Okay, so I see you tomorrow now. Okay, if there's any change, I will let you know.